Hi, I'm Stanley Roach. I'm from Onslow College, and my project is called Optical Tube. It's about looking down tubes which are shiny on the inside, such as this one, and the images and patterns formed when you do so. And the aim of my investigation was to predict and model these images accurately when a real observer looks down a shiny tube like this. So this is an example of the phenomenon occurring. So what you see when you look down a tube, there's different colours because of the things that you can see through the end of the tube. Early on in my investigation, I came up with two terms to describe the image formed. I called the sharp lines you can see rings, and the shaded areas in between bands, so that's a band there. And my basic theory was that the rings formed were actually reflected images of the end of the tube. So you can see in this ray diagram to the left how the observer is looking at the second ring, and the light is actually coming from the end of the tube. I set out to predict the relative intensity of bands. So here I wanted to predict the intensity of each of these bands as they get further out from the center. Now, what I did was basically came up with a general intensity formula based on the geometric optics of an optical tube. So IR is the relative intensity of a given band. DR is the change in intensity due to relative path length of the light. So this is a small effect, but it's still taken into account. So that's with outer bands, the light travels slightly longer, and so intensity will decrease. Theta R this is specific to each setup. There will always be a relationship here, but I experimentally determined it just for one setup. So this was the relationship I found for an aluminium tube and one type of green light. And basically, with each bounce, you lose an amount of intensity given by this relationship. So that is what to the power n here represents. So then you get this for the amount of light lost with a given reflection. So this comes up with this formula here to predict relative intensity. We put this on a graph. This is predicted relative intensity of the bands, and then we measured the relative intensity, and you can see that it's a very accurate prediction. So this is Wolfram Mathematica, and what I've done is I've taken the trigonometry I developed. You can see it in the report I developed from the diagrams there, and I've used it to make several models. So this one is a combination of a whole lot of things. The first thing it does is it shows you where, if you've got the observer at a given position, which I can adjust here, it shows where the light that the observer sees is actually coming from. So you can see by this line here that the light's bouncing around before it reaches the observer, and then it shows where it appears to be coming from. So to the observer, it looks like the light's coming from over here, and then we can adjust where the observer is looking, and we can see that these points where the light appears to be coming from, they all correspond to a point on the ring, which is one of the rings in the image form. So this is the third part of the model, the ring form. So we can adjust where the observer is and the angle they're looking at, also the number of times the light bounces, so we can get a look at each individual ring and where the light is coming from, where it looks like it's coming from, and how this corresponds to the image formed. So I used my mathematical model to predict what an observer would see looking through a slit at the phenomenon, and what it predicted was that along the axis of this slit the image will be quite distinct, and that's shown with the thin sections in this picture, and that as the image gets further away from this axis, the rings get more and more blurred and indistinct, and that's shown in the thick shaded areas, which represent the blurred sections of the rings. And you can see that the distinct sections of the ring along the axis correspond to those in the prediction, and that as the image deviates from this axis, you can see the blurred sections. So this shows that a real observer can be modelled, not just a theoretical point observer.